Hi, everyone. Your significant other may have accused you of not thinking logically. Well, prove them wrong. Section 0.2 on logic. A proposition is a statement that is either true or false. For example, I get an A in the class, or I pass the class. P and Q could be propositions here. If P then Q can be written like so, with an arrow here. If P then Q. P here is called the hypothesis, assumption, or condition. Q is a conclusion. Now, this statement, if P then Q, could itself be true or false, as we'll see. If we know it to be true, we sometimes use a double bar arrow, and we might say that P implies Q. Now, if P implies Q and Q implies P, I'll skip all the way to here. If P implies Q and Q implies P, then they imply each other, and we have logical equivalence, meaning both have to be true or both have to be false. Many definitions can be thought of as these: if and only if, or IFF statements. Okay. For example, 2x equals 6 if and only if x equals 3. If you're solving a math problem in an Algebra 1 class, you often write a sequence of equations and they're equivalent in the sense that you can reverse the arrow. And these are all true or all false. All right. Let's do an example. Consider this if-then statement. If I get an A, so that's proposition P, then I pass. I pass is proposition Q. P can be true or false. Q can be true or false. So P here is the hypothesis, assumption, or condition. Q is the conclusion. Okay, now, first of all, is this statement true or false? If I get an A, then I pass. Well, that statement is true. If you get an A in the class, then you pass. But now consider the converse of this. The converse of the if-then statement, if P then Q, is the statement if Q then P. If this is if P then Q, write the statement if Q then P. What is the converse of this statement up here? What's the converse of that statement up there? The converse will be, if I pass, then I get an A. But is that a true statement? If I pass, then I get an A? No, because we can think of a counterexample. A counterexample corresponds to a situation where the hypothesis is true and yet the conclusion is false. Can you think of a situation where you pass and yet you don't get an A? Can you think of a counterexample? Well, yeah, you can get a B or you can get a C. And these are both counterexamples where you pass but you don't get an A. And if you have counterexamples, then that means that this statement overall is a false statement. Overall, it's a false statement. Big ol' F. If I pass, then I get an A. That's a false statement. It's true that some people who pass get an A, but as an if-then statement, this is false because the hypothesis does not guarantee the conclusion. All right. So sometimes the converse is true. Sometimes the converse of a true statement is true. Other times it's not. So you have to be careful not to mix these up. In an if and only if case, you could mix them up. You can associate these things together, but sometimes the arrow matters. I'll give you a more algebra example. X equals 2 implies that x squared equals 4. I think you would agree that if x equals 2, we know that x squared has to be 4. Okay? This is a true implication, a true if-then statement. That's why we have the double arrow here, double bar arrow. But consider the converse. If x squared equals 4, then x equals 2. Does this imply that? If x squared is 4, x could be -2. That's a counterexample. That would cause the top to be true, but not the bottom. So x squared equals 4 does not imply that x equals 2. And overall, if you say x squared equals, if you say if x squared equals 4, then x equals 2, that would be a false statement. If you were to say, well, if you were to say if this, then that would be a false statement because we have a counterexample. This is a false if-then statement because there's a counterexample. So be careful. There are some situations where you cannot reverse the arrow. And these are often situations where we have to check our solutions. For example, this is related to the idea that if you have a radical equation, and if you square both sides of an equation, then in the end, you have to check your solutions. All right, anyway. So the converse of a true if-then statement could be true or could be false. Consider another example. Go to here. Consider this. A Jerry Springer example, if you remember him. If Pat is a daddy, then Pat is a man. That might be a bit un-PC, but let's accept that. If Pat is a daddy, then Pat is a man. Let's say that's true. What would the converse say? What would the converse say? The converse would say, if Pat is a man, then Pat is a daddy. Are all men daddies? Am I going to get a surprise in a couple of weeks? This is a false statement. This is a false statement. So this is a case where, again, the converse of a true statement is false. All right. So let's say that the original statement goes, if P, then Q. Here's the original statement. If P, then Q. Right? For example, remember the statement we talked about earlier. I'll shrink this. If I get an A, then I pass. If I get an A, then I pass. P says I get an A, Q says I pass. Okay, well, remember, what's the converse of the statement? If Q, then P. The inverse is if not P, then not Q, where you negate the hypothesis and the conclusion. We're not going to deal with that. I'm going to talk more about the contrapositive. Okay, so what's the contrapositive of if I get an A, then I pass? The contrapositive of if P, then Q is if not Q, that's what the tilde means. If not Q, then not P. This also represents not. This and also that, these represent not. So for contrapositive, what do? You switch and negate the hypothesis and the conclusion. Switch and negate. Switch and negate. Okay, you switch P and Q and you not both ends. What is the contrapositive of if I get an A, then I pass? Well, first off, remember the converse is if I pass and I get an A. We know that's false. The original statement is true. The converse was false because we found counterexamples. You could get a B or a C. But now what's the contrapositive? The contrapositive is going to be Okay, so again, here's the original. Here's the contrapositive. By the way, the inverse just negates the two ends, the two propositions. The contrapositive says, switch and negate. If I do not pass, then I do not get an A. If I do not pass, then I do not get an A. Is that a true statement? If I tell you you don't pass, is it possible that you can get an A? No, it's impossible. This is a true statement. If you don't pass, you don't get an A. Now, that's not a coincidence, because we have what I call the contrapositive theorem. If an if-then statement is true, such as this one, if I get an A, then I pass, then the contrapositive must also be true. If I do not pass, then I do not get an A. This Venn diagram might be helpful. Okay, so again, if you get an A, then you pass. If you're in this disk, if you're in the inner disk, you're in the outer disk. What does the contrapositive say? The contrapositive says, if I do not pass, then I do not get an A. If you do not pass, then you're out here somewhere. Then is it possible that you're in here, that you get an A? No, that's impossible. You do not get an A. If you're not passing, if you're outside the outer disk, there's no way you're inside the inner disk. If you're not passing, there's no way you're getting an A. The contrapositive theorem. If an if-then statement is true, the contrapositive is automatically true. Now, this is very valuable. Let's say that I give you 10 different math theorems. All of them are if-then statements. Really, by the contrapositive theorem, you have 20 if-then theorems, because you can take the contrapositive and get another theorem that's true. So I've doubled your theorems. You should pay me. All right. For an if and only if statement, let's say this is true. If I get an A, B, or C, then I pass. All right. Well, the converse is also true. Okay. And if the original statement and the converse are both true, well, that means we have an if and only if statement that's true. Okay. The contrapositives of both are true. They're all true. So for an if and only if statement, okay, if you take this true statement, if it's really an if and only if statement that's true, then the converse is true, the contrapositive is true, the inverse is true, all those guys are true. So you can associate P with Q. You have complete equivalence. We can say you get an A, B, or C if and only if you pass. You have equivalence. Again, dictionary definitions are typically if and only if statements. Runner, noun, one who runs. In higher math, they talk about necessary and sufficient conditions. Use your common sense, but you can parse those logically. All right, I hope you learned how to think logically, and you can now tell your significant other to go away. You can think logically now. All right, until then.